Welcome students to a lecture series on multiple integral. I am Dr. Apurba Saha, Assistant Professor, Department of Applied Science, Haldia Institute of Technology. Today I am going to discuss about double integral. So first we recall integration of a function of single variable. Integration a to b fx dx gives the area between the curve y equals to fx and x-axis for x lies between a to b if fx greater equals to 0. And we approximate this area under the graph by rectangular strips. And we already know that integration a to b fx dx equals to limit n tends to infinity summation I equals to 1 to n f of xi del xi, where xi is a point in the ith subinterval where we divide the interval AB into n number of subintervals, provided this limit exists. So for a double integral, we consider a function z equals to f of xy of two independent variables x and y defined on a region R in the xy plane. So this is your region R in the xy plane. Now we subdivide this region R into smaller rectangles, and these rectangles form a partition of the region R. Let the areas of the smaller rectangular pieces are del AI. So this is your smaller rectangular subregion, and area of this subregion is given by del of AI equals to del xi del yi. I runs from 1 to n because we subdivide the region R into n number of subregions. And let xi yi be a point belonging to the smaller rectangular region whose area is given by del ai. Now, similar to the above, we consider the sum I equals to 1 to n f of xi del ai, where del ai is equals to del xi into del yi. Now let the number of partitions n tends to infinity in such a way that the areas del ai tends to 0. Then if the following limit, this one, exists, then we say that the function f of xy is integrable over the region R with respect to x and y. And the value of this limit is called the double integral and is given by this one, where this del ai equals to del xi into del yi, and this dA equals to either dx dy, or you can say this is dx dy. So this is the definition. Now we see some properties of the double integral. Similar to integration of a function of single variable, here we see that if f and g be two integrable functions on the region R, then the double integral of f plus g dA equals to double integration R f dA plus double integration R g dA. Next one, if c is a constant, then the double integration over the region R cf dA equals to c double integration R f dA, where c is a constant. Next, if f greater equals to z at all points of the region R, then double integration R f dA greater equals to double integration R g dA. And the next one, double integration f dA over the region R equals to double integration R1 f dA plus double integration R2 f dA if R is the union of two non-overlapping regions R1 and R2. Suppose this is your region R and you have two overlapping regions, say R1 and R2, then this one holds. Now we see the interpretations of double integrals. If f is a function from R where R is a region of R2 to the set of all real numbers is continuous and f of xy greater or equals to 0, then the double integration of f of xy dA over the region R is the volume of the solid lying over the region R in the xy plane below the graph of z equals to f of xy. Next one. If f of xy equals to 1, if f of xy equals to 1 for all xy in the region R, then double integration R dA gives the area of the region R. Integral of density is the total mass, and last one, integral of charge density is the total charge. Now here the question is find the area of the region bounded by the curves y equal to x square and y square equals to x. See, we know that this curve x square equals to y and this one is y square equals to x. These two curves meets at 0, 0 point here and 1, 1 point. So this is the region R and this is shaded here. Now the boundary is composed of two curves. First one is this one. This is one curve and this is another curve. So this is your y equals to x square curve and this is your y equals to root over x curve, right? And here x is runs from here x is equals to 0 and here x equals to 1. And from the previous property we know that when f of xy equals to 1, then in double integration R dx dy, this gives the area of the region R. So here this is the region. So here first we put dy, then we should remember that we have to write the limit of y here. Now how to find the limit of y here? First we'll draw a strip parallel to y-axis. So this is a strip parallel to y-axis. Now you see this is y equals to x square and this one y equals to root over x. So this strips gives you the limit where y runs from x square to root over x. So this is your y equals to x square and this is y equals to root x and x runs from 0 to 1. So here 0 to 1. Now how to integrate this type of integrals? So first we will integrate this one with respect to y, and when we will integrate this one we will keep all other variables here only x as constant. Okay, so dy only gives you y and the limit of y is from y square to root over x dx. So this gives 0 to 1 root over x minus x square dx, that is 1 by 3. You can check this one. So 1 by 3 unit is the area of this region. Now, the double integral of a rectangular region. So in this case, we consider the region R to be a rectangular region in the xy plane. And this theorem is Fubini's theorem. Let f of xy be continuous throughout the rectangular region R. Here region R is taken as a rectangle. This is your rectangle in the xy plane. This is your R. And we let x is runs from A to B and y runs from C to D. So this is your area of integration. This is the area of integration. Then double integration f of x y dA equals to C to D integration A to B f of x y dx dy. Here we put dx first, so put here the limit of a x from A to B, and this is the limit of y C to D. And if we write dy dx, then first we'll write the limit of y, that is C to D, and limit of x, that is to B. The problem: evaluate double integration over the region R x minus y by x plus y dx dy, where the region R is given by x from 0 to 1 and y from 0 to 1. So this is the rectangular region. And from the previous one, Fubini's theorem, we have learned that the double integration over the region R x minus y by x plus y dx dy can be written as this one, 0 to 1. This is the limit of x, this is the limit of y, 0 to 1, x minus y by x plus y dy dx. So first we will integrate this one. Okay, so here we will treat x as constant. Then see, this one can be written as this one, 2x by 2x plus y minus 1 dx dy. And so for this one, 2x log of x plus y, because we treat x as constant, minus y, and here y runs from 0 to 1. Now if you put the limit here of y, then you will have this one. So this is 2x log of x plus 1 dx, 0 to 1 2x log of x dx, and 0 to 1 dx. So this becomes 0 as 0 to 1 x log of x plus 1 dx equals to 1 by 4, and 0 to 1 x log x dx equals to minus 1 by 4. You can check this one. Now, here, if we take the region R as non-rectangular regions, so what does it mean? Suppose you have a region here R which is not a rectangle, because see here y runs from g1x to g2x, that is two functions of x, and x runs from A to B. So Fubini's theorem stronger form: let f of xy be continuous throughout the region R if R defined by x lies between A to B and y lies between g1x to g2x, where g1 and g2 are continuous functions of x on the interval AB. Then the double integration R f of xy dA equals to A to B g1x g2x f of xy dy dx. So here this is the limit of y, because we write here y first. Okay, this is the limit of x into b. Similarly, here also let fx be a continuous function throughout a region R, and here this region R is defined in this way: y from C to D and x from h1y to h2y, where h1 and h2 are continuous functions on the interval ct. Then the double integration over R f of xy dA equals to C to D h1y h2y f of xy dx dy. Problem: evaluate the double integration over R root over 4 x square minus y square dx dy over a triangle formed by the straight line y equals to 0, x equals to 1, and y equals to x. So first we have to find the region R. So the region R is shown in the figure by shaded. How it is formed? See, the line y equals to 0 is this one. So this is your line y equals to 0 and x equals to 1. This is your line x equals to 1 and this is your line y equals to x. Then this is the region R. So R is composed into two lines. One is y equals to 0, that is line OA, y equals to x, that is line OB, defined on the interval x from 0 to 1. So here, see, this region R, you can write this one. X is lies between 0 to 1 and y, that is lies between, see, this is the rectangular strip parallel to y-axis, then y runs from 0 to x. So here in this case, R is the non-rectangular region. So from the Fubini's theorem of stronger form, we know that this double integral R root over 4 x square minus y square dx dy can be written as 0 to 1. This is your, see, this is your g1x, this is your g2x. This is the limit of y. Root over 4x square minus y square dy dx. So by well-known formula, so this is y by 2 root over 4x square minus y square plus 4x square by 2 sine inverse y by 2x, and the y, limit of y is from 0 to x. Now if you put first y equals to x and y equals to 0, we have this one, 3 by 2 plus 5 by 3 x square dx. So this is 3 by 2 plus 5 by 3. This is for this one, x is cubed by 3, and the limit of x is 0 to 1. So 3 root 3 plus 2 pi by 18. This is your answer. So the value of this one is 3 root 3 plus 2 pi by 8. Now see some practice set. Evaluate 0 to pi by 2, 0 to pi sine of x plus y dy dx. So for this one, first you have to integrate this one with respect to y, and you have to treat x as constant and so on. And for this one, next one, 0 to 1, 0 to x, x y dy dx, similar process. Evaluate 1 to 2, y to y square dx dy. Next, double integral r x square plus y square dx dy, where r is the region bounded by y equals to x square, x equals to 2, and y equals to 1. Next, last one, evaluate double integration over r x square plus y square dx dy, where r is the region bounded by x y equals to 1, y equals to 0, y equals to x, and x equals to 2. In the next class, we will learn about triple. Thank you.